The Set Theory Guide for Artists podcast. Better grab a coffee and settle in because we have a real treat for you today, starting with the fireplace. Immediately after the miracle of the table of contents, the artist went to an office supply store and bought 7 reams of paper. Do you think this is enough? We don't know how long the book will be. Do you think we look suspicious buying all this paper? No, it's fine. We're artistic. After they secured the paper, they got more supplies: water, tea, snacks, and extra blankets and pillows. The artist set up a study zone by the fireplace in the studio where we first saw the artist and her blank canvas, which is still blank. They unwrapped the reams of paper and set the blank paper in neat piles on the ground and situated themselves between the paper and the fireplace. What should we do? Watch the paper until the book appears? We all stared at the paper piles for a while, but of course that didn't work. Let's watch the fire and talk about something else. We watched the fire and we watched the light reflect and bounce in the artist's eyes. We are content listening to their laughter and conversation. You know who's a really good artist? Who? Van Gogh. Oh yeah, he's the best. Those trees. As soon as the man said trees, we all heard the rustling of paper, and in the first pile was Chapter 1, Part 1 of the book. They had the rest of the day and most of the weekend to read about infinity by the fireplace. After the man left, the artist was alone again and was looking fondly at some of the notes from the weekend. Is Aleph Sub Omega inaccessible? She started to focus again on her future and what to do next when she flipped the paper over and saw a note from the man. Where would you want to be most in the world? She wasn't sure if she had a specific answer to the question. Or did she? But how can I? Well, there are a lot of paths. I wonder if she thought she'd be doing this a year later. I would like to say about this that sounds like a lot of fun to be reading some proofs by a fireplace, and get some tea and some snacks. I'm all for it, and I hope that comes true. Chapter 1, Part 2. Starting with the one and only Aronszajn trees. We begin with Aronszajn trees, where the rationals really shine. Then we get a chance to see Hausdorff gaps and experience eventual domination. We will see the definition of filters and ideals, and finally, cofinality. Oh, and the image, Several Circles by Wassily Kandinsky, 1926. Aronszajn trees. Before we get to Aronszajn trees, aka Aronszajn trees, okay, it's not spelled like that, but that's how it's pronounced. Let us code the natural numbers with colors. We can think of the cardinality of the visible color spectrum from violet to red as the cardinality of the interval 0 to 1, aka the cardinality of the continuum. Each color corresponds with a wavelength, and even if our eyes cannot distinguish between two very similar colors, we can look at their wavelength to see the difference. Here's a proposal for how to have a countable arrangement of colors using the 7 main colors and black and white. We start with the 7 main colors, followed by the 7 main colors with 1 white zip. We pay homage to Barnett Newman here. His work is too young for the public domain, so it is not included here. Then the 7 main colors mixed with 1 black zip. Then the 7 main colors mixed with 2 white zips. Then the 7 main colors mixed with 2 black zips, and so on forever. This ordering is a linear ordering. A strict partial ordering is a binary relation less than, or that symbol, on a set C with the transitive property. If A is less than B and B is less than C, then A is less than C. And where for any A and C, A is not less than itself. A partial ordering is linear if for any P, Q, and C, either P is less than Q, P equals Q, or P is greater than Q. There's more than one definition of a tree in set theory. In this section, a tree is a partially ordered set t less than, where for each x and t, the set of all predecessors of x, the set of all y such that y is less than x is well-ordered, linear order where every non-empty subset has a least element. It's well-ordered by less than. We have seen the infinite binary tree with uncountably many infinite paths. Let us construct another tree of height omega where each level is finite. Every well-ordered set is isomorphic to an ordinal. So every x and t has a set of predecessors which has an order type, an ordinal that it is isomorphic to. And this is the rank or order of the node. Order of x is the order type of the set of y's less than it. Then we can define the levels of the tree indexed by ordinals. The alphth level is the set of all x such that the order of x is alpha. Then the height of the tree is, height of t is the supremum of all the orders of x plus 1, where x is in t. The infinite binary tree has height omega, since every node has a finite order and their orders are unbounded, so that the supremum is omega. The height of a tree is the least ordinal such that the tree is empty at that level. A branch in a tree is a linear ordered subset of the tree that is not contained in any other linearly ordered subset, maximal chain. The length of a branch is the order type of the branch. For example, we saw that there are uncountably many omega branches in the infinite binary tree. We will construct another infinite tree with finite levels. Will it have an infinite branch? Let us use the natural numbers coded by the colors to make the tree. This choice is getting us ready for later, where the branches of an Aronszajn tree will be sequences of rational numbers. Let T be a tree where the root of the tree is any color in C, the countable set of colors. Level 0, we pick 12 here, just some number. For the first level, choose children of the root to be any colors that are greater than the root. So anything bigger than 12. Okay. Since we want to create an infinite tree, we should continue. Not every node needs to have children, but at least one does. For the nodes that do not have extensions, let us continue to always choose greater colors so that our branches are increasing sequence of colors from the countable color set C. Level 2, following the rules. Since we are making an infinite tree, we must continue. At least one node on the second level must have an extension, and at least one of these nodes must have an extension, and one of these nodes must have an extension, and so on. Let us see that this tree has an infinite branch. To construct an infinite branch, start with the root. Then choose a successor of the root which does not lead to a dead end. That is a successor that has infinitely many successors. If there is no such node, then the tree is finite. That is, on the first level, choose a node x1 such that the set of all y and t such that y is greater than x1 is infinite. On the second level, choose a successor x2 such that the set of all y and t such that y is greater than x2 is infinite. At the nth level, choose a successor which has infinitely many successors, and so on. No matter the construction, an infinite tree with finite levels will have an infinite branch. This is Koenig's lemma. If T is a tree of height omega such that every level of T has finitely many nodes, then T has an omega branch. We might wonder, if T is a tree of height omega 1 such that every level of T has countably many nodes, must T have an omega 1 branch? The answer is no, because an Aronszajn tree is a tree of height omega 1 with countable levels which has no omega 1 branch. And we can construct an Aronszajn tree. The idea in the construction of an Aronszajn tree is what we label the nodes with rational numbers. Okay, the idea in the construction of an Aronszajn tree is that we label the nodes with rational numbers so that each branch is an increasing sequence of rational numbers, and thus no branch can be uncountable. Let us use our color scale. Then the rational number 3/5 is represented by half 3, half 5, we'll say. And since there are literally like 3 on top, 3 on top, 5 on the bottom, let's say. Wait, let us see, since there are equivalent fractions to 3/5, such as 6/10, there's multiple ways to represent one rational number. Let us see that the rational numbers are countable by finding a countable list of the rational numbers. The figures below illustrate that the positive rationals are countable. And similarly, the entire set of rationals is countable. We are overcounting since we will count each equivalent fraction, but even with our overcounting, the result is still countable. If we go down any row or column, we might not come back. So we will work the finite diagonals to make a path which encounters every rational. So we make this path for the rational. Thus, the set of rational numbers is countable. Therefore, when we construct an Aronszajn tree, where the branches are increasing sequences of rational numbers, we cannot have an uncountable branch. An Aronszajn tree is a tree of height omega 1 which has countable levels and no uncountable branch. Constructing an Aronszajn tree. Let the 0th level of the tree be u sub 0 is this let me just, you guys, I think I just mean the empty set, right? I think I just meant the empty set, not the set that contains the empty set. Oh, I'm sorry. I'm so sorry. I'm not understanding my own. So the 0th level of the tree, it has just one node, and that is the empty set. Okay, so that is the symbol for the empty set. It's just, I didn't even put that in the list, but we'll say 0 is just a white circle there. Okay. For the first level, extend all positive rational numbers. It is okay if we are using multiple representations of each reduced fraction. So u sub 1 is the set empty set R, where R is in, it's just all the rationals, all the positive rationals. For the second level, extend each x in U1 by all rationals greater than it. So the second level of the collection of sequences. So x2 is x adjoin R, where x is in U1, R is a positive rational, and R is greater than x. Like we did for the conics. For the third level of the tree, extend each x in U sub 2 by all rationals greater than it. So the third level is a collection of all sequences. U sub 3 is x adjoin R, x is in U2, R is positive rational, R is greater than x. This tree might look finite, but below each node there are infinitely many nodes. We define the levels of the Aronszajn tree by transfinite induction. Transfinite induction is like induction on the natural numbers, but it is on the ordinals, and so we must also consider limit stages. Let's continue the construction of the finite levels. Given level u sub n, let u sub n plus 1 be the set of all x adjoin R, where x is in u sub n, R is a positive rational, and R is greater than x. Be all the rational extensions of every node in u sub n. So u sub n plus 1 is all the rational extensions of every node in un. If u sub n is countable, then u sub n plus 1 is countable, since each node in un has countably many rational extensions, since the rationals are countable. Also, each level u sub n constructed so far has the property that for every k less than n, also, each level u sub n constructed so far has the property that for every k less than n, and every x in u sub k, and every r greater than the sup of x, there is a y in u sub n such that x is a subset of y, and r is greater than or equal to the sup of y. So far, our nodes are finite sequences, but at later stages, we will have to think about supremums of infinite sequences of rational numbers. For example, let n equals 4, and consider our node 1/2 on the first level of the tree. Take any rational number greater than 1/2, such as 1. The midpoint between these two numbers is 3/4, and we can continue in this way to make a sequence of any length that will still be below 1. Suppose we want to make a sequence of length 5. We could do empty set 1/2, 3/4, 7/8, 15/16. Then x equals empty set to 1/2 is a subset of y equals MC set 1/2, 3/4. So y is this extension we're looking for, 7/8, 15, 6. And sup of y is less than 1. And we can see in the picture that might look like. Then in the tree, y is an extension of x on the 4th level. And they're sort of like following the 1. They want to still say less than 1, but it's kind of guiding them. This is like, it says follow me. It is like the q greater than sup x is a caret leading us to create a sequence of any length to get an extension of x at any level above x. This property holds because of the density of the rationals and because we are taking every possible extension at every successor level. So far we have built all the finite levels of the Aronszajn tree, and they are all countable, and we have the caret leading us to create an extension at any level property between them, which we will prove by induction. We are at the crucial moment where we construct u sub omega, the first infinite level of the tree. The tree t sub omega that we have built so far has continuum many paths, so we cannot extend every branch to the omegeth level. While there are uncountably many paths in t sub omega, and I wonder if that should be t sub less than omega. There are countably many nodes we will choose for each node only countably. While there are uncountably many paths in t sub omega, there are countably many nodes, and we will choose for each node only countably many extensions to the omegeth level. Countably many nodes times countably many extensions is still countable. So if we can do this, we construct the first infinite level of the Aronszajn tree. For each x in t sub omega and every r greater than x, choose an omega sequence of y of rationals that contains x and whose supremum is less than or equal to r using the density of the rationals. For each node and each rational number greater than the sup of the node, choose one y. Then let the omegeth level be the countable collection of these y's. For each path we want to extend to the omegeth level, we need to put a rational on the omegeth level. In the image, we just use the rational which guided us. The rank of a node is the order type of its predecessors, so we will actually put a node on the, until we actually put a node on the omegeth level, it is empty. Then for the next level, we take all rational extensions of nodes on the omegeth level. U sub omega plus 1 is the x adjoin r, where x is in u sub omega and r is greater than x. Given any alpha less than omega 1, if u sub alpha has been constructed, let u sub alpha plus 1 be the x adjoin r, x is in u sub alpha, r is greater than x. Then if u sub alpha has the caret leading us property, so does u sub alpha plus 1. And if the alpheth level is countable, so is the alpha plus 1th level. We can prove these with transfinite induction, and we will know the limit levels will hold by construction below. If alpha is a limit ordinal where the levels below have been constructed, we want to construct the alpheth level so that the property holds and it is countable. Let x be in t sub alpha. Then since alpha is countable, there is a sequence alpha sub n equals 0 to infinity, where x is in u sub alpha sub 0, such that limit as n goes to infinity, alpha sub n equals alpha. Then for each r greater than x, there is a y sub n in u sub alpha n, such that x is a subset of y sub n, and the supremum of y is less than r. Let y be the union of these y sub n in omega. And let u sub alpha be the collection of all such y for each x in t alpha. At successor stages, take every possible rational extension. At limit levels, for each node already constructed and for each rational greater than it, choose a path to the next limit stage. Finally, the Aronszajn tree is the union of all the levels created. T is the union of alpha less than omega 1 u sub alpha. Each level will be countable, but there's also no uncountable branch because there's no uncountable sequence of rational numbers. So here's the full Aronszajn tree. Big idea. We lay down the tracks for every possible route at successor steps so that for each node we can choose countably many paths to extend to the limit when we get there. In the end, we get a tree of uncountable height with countable levels and no uncountable branch. There is a large cardinal property inspired by Koenigslemma and Aronszajn trees called the tree property. A cardinal kappa has the tree property if any tree of height kappa with levels of size less than kappa has a kappa branch. We have seen that omega has the tree property while omega 1 does not have the tree property. Okay, so I'd like to say for this section, I was really excited to do this section, but the first time I gave a talk like at a set theory seminar when I was in grad school was I gave a talk about, or maybe one of the first, I gave a talk constructing an Aleph 2 Aronszajn tree, which depends on if it holds, if you can get one if CH holds, or maybe GCH, sorry. So this was along the way, I had to look at this proof to figure out the Aleph 2 proof. And this proof is ENIAC. And I would say that I really like Aronszajn trees or trees of any kind, and like colors. I've always wanted to like make or just talk about how the reals are the colors are uncountable. Like the colors are the continuum of colors. It's just like the same size as the real. I just want to like say that in a book or something. So I made these, and also the rationals. It was hard to make these. They took forever because I just did everything by hand. And I would like to say that when I was at the University of Kansas, I couldn't remember if it was Kansas University of Kansas. Yeah, I was KU. I got a master's in math there, and there was a room there that was we called it the Aronszajn room. We called it the Aronszajn room or something like that. And it was a room where there's this blackboard, what we called Aronszajn, wrote on this blackboard. It was like preserved blackboard. So I've written on the blackboard that Aronszajn, and it's actually pronounced Aronszajn. I had no idea who Aronszajn was or anything like that when I was getting masters. When I was studying my masters, I liked complex analysis, and so later when I started studying set theory, I saw that name again. I was like, what? That's so familiar. But then I found out that it's called Aronszajn, and I just felt an immediate connection to it, and so I kind of felt like I was rock star up here with this section, because it's still hard though. It's always so hard to like read the proof and stuff. But so I really like this section and hope you enjoyed it. And we'll see you next time.